This video is about the electromagnetic induction. First is about the magnetic field and magnetic flux. Second part about Faraday's and Lenz's law of the electromagnetic induction. Third part is the power transformers. First, we talk about the magnetic field. This is for a ball magnetic magnet. The magnetic field is about this. This is N, this S. Magnetic field. This is the magnetic field for the ball magnet. Uh, for a current, and this will have a current I. They have the magnetic field using the red hand rules. Magnetic field is this position. This is the magnetic field. For a loop of the circular loop of wires, have the magnetic current. Use the right hand rules. Have the magnetic field is that this one. Use the red hand rules. This is the magnetic field. This magnetic field for the long wires. This is the loop of wires. Uh, for electric current in the magnetic field, they have the force. Use the right hand rules. First, the forefinger point to the current, then turn 90 degree to the magnetic field direction. The force is the sum. So this is the force here. This is the current. This is the magnetic field here. Uh, for current carrying wire in that magnetic field, the force, we can use that the force that the B can divide into this mm, This is the B sine theta. B sine theta. This is the electric current in the magnetic field. For example, a loop hinged from a balance which measure the downward force when the wire current. What is the magnetic field of the magnetic B? From here we can, this current, we can because the current equals to B L I, so B equals to F divided by L I. The force is the 3.48 10 to minus 2 Newton. L is the 10 centimeters, is about 1.1. And I is the 0.245 I. The B equals to 1.42 Tesla. For a electric charge moving in the magnetic field, for the positive charge, we first use the forefinger, point to the moving direction, then turn 90 degree to the magnetic field direction. Thumb is the direction force. This force is downwards force. For an electron moving in a uniform magnetic field B is the inner page, the electron moving direction to the right. So the force is downwards, is pointing to the center. What's the force? Equal to MA. This force is the QVB equals to M. R is the diameter of the circle path. So the R equal to MV QB QB. For the magnetic flux, this is the a loop of wires. This is the magnetic field B. The flux is the magnetic field in the loop, through the loop. So the flux of magnetic flux is the B perpendicular to the loop. This is for the B unit is Tesla, A is ampere. Magnetic flux is the Weber. So 1 Weber equals to 1 Tesla times A ampere. For the Faraday's and Lenz's law of electromagnetic induction, Faraday's law of induction means the induced EMF is defined as the flux change through the loop over a brief time intervals. The induced EMF equals to this is the Faraday's laws, and this minus sign. The minus sign reminds the direction of induced EMF act is oppose the original change of the flux. This is the Lenz's law. Lenz's law. A current produced by an EMF moves in directions so that its magnetic field opposes the original change in the flux. This is a loop in the magnetic field A from A to change B. This is because the flux equals BA, because the A decrease, so the flux is decreased. For the magnetic flux decreased, the induced flux in the induced magnetic field in same direction of the original magnetic field. The same directions, then we can decide the induced current, use the right hand, the same directions. So the current in these directions, clockwise, in the clockwise directions. For the Lenz's law, first step is to determine whether the magnetic flux inside the loop is increasing or decreasing or unchanged. First, determine original magnetic field in the loops. Then the magnetic field due to the induced current, due to the induced current, point in the same direction as the external field if the magnetic field phi b is decreased. Point in the opposite direction as the external field if the phi b is increased. Once you know the direction of the induced magnetic field, use the right-hand rule 1 to find out the direction of the induced current. We must remember there are two magnetic fields. One is the external magnetic field, phi b, determine phi b is decreased, increased, or unchanged. Then another is the magnetic field produced by the induced current. if the phi b is uh, increase, the induced magnetic field is in the opposite direction. It's increase in opposite direction, in the decrease in the same directions. So we can determine the magnetic field produced by the induced current. Then use the right hand rules to determine the induced current. Induced current. Now we see an example. A square coil where the side is the 5 centimeters contain 100 loop. This is N equals to 100. It's L equals to 0.5 centimeters. B is the 0.6 T. At T is the 0, the loop H is in the same edge of the magnetic field. It takes the 0.1 seconds for the coil. All the coil move out, move in this position, move to the field-free regions. The coil resistance is 100 ohm. Find the rate of flux change through the coil and the EMF and I. So the solution, we first found the phi b equals BA equals to 0.56 T. A is the squared equals to 1.5 times 10 to minus 3 Weber. The change of the flux is the delta phi b, delta T. In this position, the flux is 0 minus equals to minus Weber per seconds. So the EMF equals to minus N equals to 100 times 0.1 seconds means is equal to 1.5 watts. Find the current VBR 100 ohm equals to 15 mu mn ma ma. This is the solution. For the EMS induced by moving conductor, the conductor move to the right, the phi B in the loop is increased. So the induced magnetic field is in opposite direction. So the current in opposite direction is into the paper. So the current means in these directions. In these directions. The EMF induced by is this one. Phi B is B delta A divided by delta T is equal to BLV. BLV. The force on the particle, if is the positive particle, the force is downwards. So they induce the magnetic field E is also downwards. Because the E is the equals to F divided by Q. F is the QVB divided by Q is equal to VB. A changing magnetic field induces an electric field. Last part is the power transformer. Because we know that this is the primary coil, this secondary coil. Because the Vs, the turns, the flux, the change rate. Because this part is equal. So the voltage ratio equal to the ratio of the turns, secondary Vs divided by Vp equal to Ns divided by Np. Since the P equals is the product I and the voltage, so the Is divided by AIP equals to NP divided by NS. The ratio of secondary to the primary current is the inverse ratio of the turns.